Hey everyone, Mr. Houck here. In today's video, we're going to continue looking at inverse trigonometric functions, and we're going to look at solving inverse trigonometric functions on the unit circle. By the end of this video lesson, you should be able to find an inverse trig function value using the unit circle and use inverse trig functions to solve application problems. Let's go ahead and get started here. So recall from the previous video, we were talking about sine, cosine, and tangent and their inverses and how we have to have domain restrictions so that sine, cosine, and tangent can have inverses. If we don't have those domain restrictions, well, sine, cosine, and tangent, they can't have an inverse. So the way that we talked about it working is both sine and tangent are restricted to the domain negative pi over 2 to pi over 2. So they're restricted to quadrants 1 and 4. And the cosine is restricted to quadrants 1 and 2, where the angle is restricted to between 0 and pi. Okay? So one question that pops up is, what happens if an angle is not in the restricted domain? Let's say that, for example, we're working with sine, and maybe we get one of the angles over here in quadrant 2. Well, in order to alleviate that problem, we would just use a coterminal angle that is in the restricted domain. So remember that you can add or subtract 2 pi to whatever angle you're working with, and you're going to get a coterminal angle. So you would add or subtract 2 pi, whichever is necessary, until you get an angle that is in the restricted domain for that trigonometric function. Okay? Also, let's talk real quickly about inverse trig functions with a calculator. So just making sure, this section is more so to make sure that we know how to use a calculator if we need to. I'm going to be using Desmos here, so I'm going to pull that up split screen. Now, one of the important things here is that if we are using a calculator, to make sure that you're in the correct degree measure. So for all of these problems, we're going to be using radians. And honestly, unless you see a degree symbol or unless you are told to answer in terms of degrees, we are always going to use radians. So on Desmos, I'm just going to check real quick that I'm in degrees. I can see that radians rather, and I can see that radians is highlighted. So we're good there. So let's go ahead and find the inverse sine of 0.1, and that's going to give me 0.10. It also tells us to round to the nearest hundredth, which is 2 decimal places. So we're going to have 0.10. So the inverse sine of 0.1 is 0.1, rounded to 2 decimal places. Okay, let's try the inverse cosine of 7/8. So again, Desmos, we're already set to radians. Let's do inverse cosine, 7 divided by 8. And that's going to give us, if we round to the nearest hundredth, so 2 decimal places, 0.51. So the inverse cosine, get shape recognition off there. The inverse cosine of 7/8 is 0.51. And then one last little problem here with the calculators, we want to find the inverse tangent of negative 0.4. So back into Desmos, inverse tangent, negative 0.4, and we get negative 0.38. So the inverse tangent always forget that shape recognition. Inverse tangent of negative 0.4 equals negative 0.38. Now, one thing that I want to remind you is what we're actually doing here. When we ask ourselves, for example, what is the inverse sine of 0.1, we're asking ourselves, what angle, if I take the sine of that angle, is going to give me 0.1? So we want to make sure that our answers are within those restricted domains. Recall that sine is restricted to negative pi over 2 to pi over 2. And when you think of pi over 2, that's about 1.57. So 0.10 is in between negative pi over 2 and pi over 2, so that angle is fine. Looking at cosine, we want cosine to be restricted between 0 and pi. So again, this is asking, what angle, if I took the cosine of that angle, would give me 7/8. Well, if I took the cosine of 0.51, I would get 7/8. and 0.51 is within this restriction. And then lastly, which angle could I take the tangent of to get negative 0.4? Well, negative 0.38 is within the tangent restriction, negative pi over 2 to pi over 2. So all those angles are within the correct restricted domain, so everything looks good there. So let's close Desmos for now. We'll come back to it here in just a few minutes. Let's look at these inverse trig functions from the unit circle. So we want to find the exact values of each expression using the unit circle. We are going to not use the calculator, and we're going to provide all answers in radians. So a couple reminders here. Remember that x comma y is cosine theta sine theta. So cosine is the x value, sine is the y value. And also, just as a reminder, I'm writing up here at the top our trigonometric domain restrictions. Again, sine is restricted to negative pi over 2 to pi over 2, cosine is restricted to 0 to pi, and tangent is restricted negative pi over 2 to pi over 2 as well. Okay, so a couple things that I think we need to go over real quick before we start looking at this is when we look at sine and tangent, we have that negative pi over 2 to pi over 2. So, we know from this little figure right here that all of this is part of the restricted domain, but we need to represent it in terms of negative angles, at least for quadrant 4. So one thing that we can do is just kind of annotate our little unit circle here. So I'm going to go ahead and say, okay, well, I have 11 pi over 6, but what would 11 pi over 6 be in terms of a negative radian measure? Well, if I use coterminal angles, if I subtracted 2 pi from 11 pi over 6, this would give me negative pi over 6. If I had 7 pi over 4, well, 7 pi over 4, if I subtracted 2 pi, would be negative pi over 4. And then 5 pi over 3, if I subtracted 2 pi, would be negative pi over 3. Okay? That's going to help us when we work with the sine and tangent. So the first problem says, find the inverse sine of negative square root of 2 over 2. And what that's really asking us is, what angle theta could I take the sine of that angle and get negative square root of 2 over 2? So again, sine is restricted to negative pi over 2 to pi over 2. So we're looking right here, quadrants 1 and 4. And we're looking for a sine value of negative square root of 2 over 2. Well, I see one right here, negative square root of 2 over 2. And that is at negative pi over 4 radians. So our answer here is negative pi over 4. That's the angle that if we took the sine of that angle, we would get negative square root of 2 over 2. And it's within the restricted domain. Now looking at cosine, the inverse cosine of square root of 3 over 2, again, what that's really asking us is what angle could I take the cosine of to get the square root of 3 over 2? And let's also remember that cosine is restricted on the domain 0 to pi. So cosine is restricted to quadrants 1 and 2. So I need to find an angle in quadrants 1 and 2 that gives me a cosine value of square root of 3 over 2. Well, I can see one right here. Square root of 3 over 2 for the x value, and that happens at pi over 6. Oh, it looks terrible. Let's try that again. Yeah, better. All right. Then lastly, we want to find the inverse tangent of negative square root of 3. So again, that's asking us what angle could I take the tangent of to get a tangent value of negative square root of 3. Well, remember on our unit circle here, all the ones in boxes represent the tangent values. And remember that for tangent, we are restricted to the domain negative pi over 2 to pi over 2. So we are looking here in quadrants 1 and 4. So which angle gives me a tangent value of negative square root of 3 in quadrants 1 and 4? Well, that's happening right here at negative pi over 3 radians. So we would get negative pi over 3. All right, For our last example problem, we're going to look at an application of inverse trig functions. So we have a ball attached to a string, and you'll see many different examples of things like this in physics. So two physics students set up an experiment with a spring. In their experiment, a weighted ball attached to the bottom of the spring is pulled down 6 inches from the rest position. It rose 6 inches above the rest position and returned to 6 inches below the rest position every few seconds. The equation h equals -6 cosine pi over 2 times t accurately models the height above and below the rest position. When will the ball first reach a height of 3 inches? So let's kind of analyze this and break it down here. So a height of 3 inches. Well, this tells me, first off, that h is going to be equal to 3. Okay? H is going to be equal to 3. So I'm going to take my function, my cosine function, and I'm going to replace h with 3. So I get 3 equals -6 cosine pi over 2t. And now we're going to work on trying to isolate for t, because that's what we're trying to find. We're trying to find a when. When is a time, so we're trying to isolate for time. Well, let's divide both sides by -6. So if I divide 3 by -6, I'm going to get -1/2. On the right side, the -6 will cancel once we divide it away, and all we'll have left is cosine pi over 2 times t. Well, we know that in order to get rid of that cosine, we need to take the inverse cosine. So we're going to take the inverse cosine on both sides. On the left, we'll get inverse cosine of -1/2. On the right side, cosine and inverse cosine will just give us pi over 2t. And now we can use our unit circle. So what angle, and remember cosine is from 0 to pi, so what angle between 0 and pi will give me a cosine value of -1/2? Well, if I'm looking at my unit circle, here's a cosine value of -1/2, and it's in our restricted domain 0 to pi. So that angle is 2 pi over 3 radians. So the inverse cosine of -1/2 is 2 pi over 3. 2 pi over 3 is equal to pi over 2 times t. So far we've gone here to here, here to here, here to here. Let's continue our work right over here. So if I want to isolate for t, I can multiply both sides by 2 over pi, which is the reciprocal of pi over 2. So now I have 2 pi over 3 times 2 over pi is equal to t. And then lastly, we just look and see what's going to cancel. So I can see that pi will cancel, and I'm going to get t is equal to 4/3. Okay, t is equal to 4/3 seconds, because our unit of time is seconds. So there's actually a way for us to determine if our answer here is correct. First, we can estimate it. So notice I provided a graph of this cosine function, and we wanted to find the time when the height is equal to 3. Okay, so if I look here, now we can't tell exactly, but we can estimate that the height of 3 is probably about right there-ish. Okay, again, we're estimating here. So when would the height of 3, or when would the spring, or the ball attached to the spring, rather, first reach that height of 3? Well, it first happened right there. And again, we don't know exactly what that point is, but we know that it's probably it's pretty close to 1. Okay, it's pretty close to 1, and we can see our time is 4/3 seconds, which is 1.3 repeating seconds. So we have a pretty close estimation there. But let me show you how Desmos can actually get a perfect answer for us. Okay, so let's hop right back over to Desmos. Okay, so in Desmos, and let me clear out some of my work here. The first thing I'm going to do is I'm going to put in the function. And instead of using h and t, I'm going to use y and x. So I'm going to let y equal h. So y equals -6 cosine pi over 2t. And instead of t, we're going to use x. Again, we're just using variables that Desmos is very comfortable with. And notice that we're going to get, and I'm going to go ahead and center our graph here, and we get our little cosine function. But if I go into my second equation and I know that I want the height to be 3, the height to be 3 inches, well, remember that we're calling y h. So if I set y equal to 3, then Desmos is going to take that horizontal line and basically intersect it with our cosine function. And all I have to do is take my mouse or your finger if you're using Desmos on your phone, click on that first point there, and it's going to tell me that the intersection of the cosine function and that horizontal line is 1.3 repeating, which is exactly what 4/3 seconds is.